Okay, we're back. So this is Atwood's machine part 2. Let me just review with you then the first one, since I have a whole 10 minutes here, and the second one is not going to take me all that time. Let's do this again. You might pause this video to see if you can get the answers before I show you these. But this is just a quick review, a little repetition. So usually the string would be a little longer to let the system go, but let's just make this 8 kilograms and this 2 kilograms. Can you see if you can find the acceleration of, say, the 8 kilogram mass? And then tell me what the tension is in the rope that connects the two. Okay, go ahead and pause this and then come back. All right, well, let's see if you got this right. I'm thinking that we have a system where there's 80 newtons down if G is 10 meters per second squared, not 9.8. And then 20 newtons. I should really draw this one much bigger. Like 4 times bigger than that. Okay, now if I straighten that out, I'm going to have, for the whole system, A is going to be 80 newtons minus 20 newtons all over 10 kilograms. It's the whole system that's being accelerated. And so that gives me an acceleration of 6 meters per second squared. Hey, this is accelerating at 6, this is accelerating at 6. So if I want to know what the tension is, maybe I'll circle this guy, and I'll say A equals F net. The F net on that 2 kilogram one is, Ft is winning because it's accelerating up, Ft minus 20 all over 2 kilograms. Let me just draw that one more time. So if this is 20 newtons down, this is Ft up. This thing is accelerating up, so Ft has to be bigger than 20. And so that's why I put Ft minus 20. And notice I'm not using 10 down here, I'm using 2. So the Ft, let's see, I bring that over, that's 12 newtons. The only way that can be 12 newtons if this is 32 newtons. I want you to notice something here. The tension is always going to be bigger than 20. It's got to be bigger than this one, but smaller than that. If you ever do this and you get an acceleration that's, if you ever do this and get a tension that's bigger than the bigger mass's weight, it's not right. The tension will always be between these two weights. If you think about it, it has to be that way. Even if you don't think about it, it has to be that way. Okay, going back to this. Now let's take a look at this type of a problem. This is pretty much the same type of problem, except when you have a table involved, call that M1 and M2. I want you to see something. With M2, you might have M2 times G, but there's a normal force from the table that's negating that. And so those two cancel each other out. Boom, boom, they're gone. And so the only force on your system, this is actually an easier problem, if you see that, is M1G. So let me find the acceleration. The acceleration is going to be the net force on the system divided by, now be careful here, the net mass of the system is M1 plus M2. The reason that we're using this as our system, that whole thing as our system, is because then the tensions, see Ft and Ft, those two tensions cancel each other out. We don't know what Ft is. And so if I use the whole thing as my system, then those two cancel each other out, and the only external force on this system that doesn't cancel is m1g. Okay, let's do one of these with real numbers, because we're real people. Okay, so here goes. Make up some numbers here. By the way, I'm assuming that there's no friction on the table. Friction doesn't complicate things too much. But let's make this 2 kilograms and this 8 kilograms. What will be the acceleration of the system? What will be the tension in the string? Okay, the acceleration of the system will be, let's see, there'll be 80 newtons down, but that will cancel with 80 newtons up. There'll be 20 newtons down, and that won't cancel with anything. If you remember, the tension forces are canceling out. The tension here will cancel the tension here, because tensions are the same. And so my acceleration is going to be 20 newtons divided by the mass of 10 kilograms. That's 2 meters per second squared. Okay, now if I want to know the tension, I'll just look at one thing. I don't want the tension to cancel out, so I'm going to look at just that as my system. Well, I already know the acceleration. The acceleration is 2 meters per second squared. So A equals the net force. Now, what's the net force on this guy? Well, we have an 80 down and an 80 Newton force up, but those cancel. I'm thinking the net force is Ft all over the mass of 8 kilograms. That's my system. I'm tunnel visioning on that. And so it looks like Ft is 16 newtons. You might ask, hey, could I have used this one? Sure. Dot that one. I say A. So A, that's 2 meters per second squared, equals F net. Well, the F net this time, there's two forces on this. There's a 20 Newton force downward and an Ft up. So that's 20 newtons down minus Ft up all over. What am I going to divide by? 2 kilograms. Solving for this, that becomes 4. Well, by golly, Ft is 16 newtons. It doesn't matter which one we look at. You see how that all works out? Why don't you try one? Since we have about 2 minutes, try this guy. Tell me what the acceleration, tell me this would be with no friction. Friction, adding friction is no big deal. Let's make this 1 kilogram and 4 kilograms. What will be the acceleration of this system, and what will be the tension in the cord? Why don't you go ahead and try and work it out? Pause this for a second and try and work it out yourself. See you in a bit. Okay, we're back. This is what I got. I said that the net force on this system is 40 newtons. And the net mass of the system is 5 kilograms. So that's 8 meters per second squared. By the way, Atwood's machines like this can never be greater than 10 meters per second squared. You will never get these to accelerate more than 10 meters per second squared. Because if I cut the string, that's the maximum acceleration this can have, is 10 meters per second squared. Okay, what's the tension in the cord? The tension in the cord is, I'm just going to go 8 meters per second squared. I might look at this one. I'm running out of time. That's the easier one to look at. So the acceleration of that is equal to the net force on that, which is just Ft for that, divided by 1 kilogram. So the tension is 8 newtons. The tension will never be bigger than the mass, the weight of this. It won't ever be bigger than 40 newtons. If it was, that would be weird. If this were 40 newtons and this were bigger, how is that accelerating downward? Okay, see ya.